Hey, and welcome to another science lesson. And today we'll be looking at the mole. And the outcome for today's lesson is that you'll be able to describe what a mole is and its links with Avogadro's constant. And so the key words for today's lesson is a mole of something is 6.02 times 10 to the 23 of it. The mass of a mole of a substance is its relative mass expressed in grams. And the relative formula mass of a substance is the sum of the relative atomic masses of all the atoms in the formula. And Avogadro's constant is the number of particles in 1 mole of a substance, which is 6.02 times 10 to the 23. Okay, so let's get started and let's first of all start looking at the mole. Okay, so specific words can be used to indicate a defined number. So for example, we use a pair of socks to indicate 2. We use a dozen eggs to indicate 12. And we use a score of markers to indicate 20. And a gross of coins indicates there are 144 coins. And a ream of paper indicates that there are 500 papers. Okay, so chemists constantly measure substances using their volumes, masses, or concentration. And those measurements help chemists keep track of particles, both those that react and those that are products. The mathematical relationship between particles in a reaction is shown using a balance symbol equation. So, for example, here we have 2 molecules of hydrogen gas, and here we have 1 molecule of oxygen gas, and these react together to produce 2 molecules of liquid water. Okay, however, particles are so tiny that more often than not, more than 1 particle of a substance reacts at a time. Okay, so the term mole represents a very large number, and that number is 602 billion, 214 million, and 76,000 billion. So we simply say 1 mole. It can be written in standard form as 6.02 times 10 to the 23. And the symbol for the unit mole is mole. And if you counted 1 apple every second, it would take 11 billion 900,000 years to count a mole of apples. Okay, that's over 2.6 million times older than the planet Earth. Okay, so 6.02 times 10 to the 23 rings of donuts would cover the surface of the Earth to a depth of 5 miles. And that's only about 0.5 miles shorter than Mount Everest. So we can see it's a very large number. And where did this number or this value come from? It came from a renowned scientist, Italian scientist called Amadeo Avogadro. In 1811, he suggested a link between the volume of a gas and the number of particles found in it. And then in 1971, an international group of scientists agreed that 1 mole of carbon atoms exactly equaled 12 grams of carbon. And this value was referred to as Avogadro's number. Okay, so a mole of carbon, 12 atoms, that's 6.02 times 10 to the 23 atoms, has a mass of 12 grams. Okay, so the mass of 1 mole is equal to the relative atomic mass of that substance measured in grams. So using this definition meant that the number of particles in a mole was based on an average relative masses and had to be determined experimentally. So if we said a tennis ball has a mass of 57.6 grams and you had 12 tennis balls, so that would in total have a mass of 691.2 grams. And if you had a mass of one basketball was 5.65 grams and you had 12 basketballs, you would have a mass of 6,780 grams. You would still have 12 tennis balls and 12 basketballs, but notice their total masses are different. And this is the same with elements. Their atom masses are completely different. But if you weighed out a mole of each of the elements, you would still have the same number of particles in that different mass of each element. Okay, so despite there being the same number of tennis balls and basketball, the masses of a dozen of each is different as they have different masses. Okay, so the atoms of different elements have different relative masses. So 1 mole of 2 different elements have different masses. So for example, here we have carbon, which has atomic mass of 12. If you was to take 1 mole of carbon, you would weigh out 12 grams of it. And with magnesium, if you was to, magnesium has a mass of 24. And so if you was to take 1 mole of magnesium, you would weigh out 24 grams of it. And with argon, if you were to take 1 mole of argon, you would weigh out 40 grams of it. And in that 12 grams of carbon, 24 grams of magnesium, and 40 grams of argon, you would have precisely 6.02 times 10 to the 23 atoms of carbon in 12 grams and 6.04 times 10 to the 23 atoms of magnesium in that 24 grams. And in 40 grams of argon, you would have 6.02 times 10 to the 23 atoms of argon. Okay, so the relative atomic mass is a comparison scale with no units. And the ratio between the relative atomic masses of 2 different elements is the same as the ratio of the masses of 1 mole of these elements. Okay, so here you can see that helium has a relative atomic mass of 4 and carbon has a relative atomic mass of 12. The carbon atom is 3 times heavier than the helium, and its a mass of 1 mole is for the helium is 4 grams, and its mass for the carbon is 12 grams. So the molar mass is 3 times the carbon molar mass is 3 times heavier than the helium molar mass, which is the same with the relative atomic mass. The carbon relative atomic mass is 3 times heavier than the helium. Okay, so let's see what we understand about the mole. Which pairs of samples contain the same number of atoms? And you may select more than one answer. And so if you said B and D, you're absolutely correct. 12 grams of carbon is 1 mole, and 24 grams of magnesium is also 1 mole. And they would both contain the same number of atoms. And 24 grams of carbon and 48 grams of magnesium is actually 2 moles of carbon and 2 moles of magnesium. And again, they would also contain the same number of atoms. Okay, so 2018, a community of scientists representing over 60 countries agreed to change the official definition of a mole. Okay, so we remember that in a mole, you've got 602 billion, 214 million, and 76,000 billion particles, which can be written in standard form as 6.02 times 10 to the 23 particles. So rather than being defined by average relative masses, a mole now represents a constant number, and it is known as Avogadro's constant. So we refer to a mole as Avogadro's constant, and it has the unit moles to the -1, which means per mole. Okay, so a particle depends on the structure of the element or compound. So when we are working out moles, it's often important that we understand what we are referring to. Are we referring to the atoms, or are we referring to the molecules, or are we referring to the formula unit? The formula unit could also be in ions. Okay, so because the particles can be atoms, molecules, or ions, or any other particle, it's important to clarify what is being counted. Okay, so with elements, you have metals and non-metal elements, and the metals can be a giant metallic structure, and the non-metals can be monoatomic or giant covalent or simple molecular structure. And these particle types could be atoms or molecules, and compounds can be non-metal, non-metal and non-metal, and metal and non-metal. And the non-metal and non-metal can be simple molecules and also giant covalent. And the metal and non-metal can be giant ionic lattice. Okay, and these particle types could be formula units. Okay, so let's see what we understand about moles so far. Which statement describes the number of particles in 1 mole of magnesium? And if you said A, you're absolutely correct. 6.02 times 10 to the 23 is a mole of magnesium atoms. And which statement describes the number of particles in 1 mole of oxygen? And if you said B, 6.02 times 10 to the 23 oxygen molecules, that is 1 mole of oxygen molecules. And you could also say D, 12.04 times 10 to the 23 is 1 mole of oxygen atoms. Because in an oxygen molecule is a diatom. It is made up of 2 oxygen atoms. So you effectively have 2 moles of oxygen atoms present. And which statement describes the number of particles in 1 mole of sodium chloride? And if you said C, you're absolutely correct, because 6.02 times 10 to the 23 formula units. Okay, sodium chloride is NaCl, so that means there's 1 ion of sodium and 1 ion of chloride that makes up sodium chloride. So if you was to, you basically would have in 1 mole, you would have 6.02 times 10 to the 23 of the sodium ion and the chloride ion. Okay, so match each term to the correct description. So atoms are the smallest part of an element that can take part in a reaction, and molecules are a particle consisting of 2 or more atoms chemically joined together. And then formula unit is the lowest whole number ratio of a compound with an ionic bond. Okay, so if we can complete this table and write the formula for each substance listed below. So the first one is sodium chloride. And so the formula of sodium chloride is NaCl. And the formula for oxygen is O2, because oxygen is a diatom. And for magnesium, it is Mg. And carbon dioxide formula is CO2. And helium formula is He. And carbon formula is C. And silicon dioxide is SiO2. Okay, and if you got all those correct, then well done. Okay, so let's now classify the particle types for each substance in the table. So previously we wrote the formulas, and now let's classify the particles. Are they atoms, molecules, or formula units or ions? Okay, so for sodium chloride, it's a formula unit, which is made up of sodium ions and chloride ions. And for oxygen, it is a molecule. And for magnesium, it's an atom. And for carbon dioxide, it's a molecule. And for helium, it's an atom. And carbon also is an atom. And for silicon dioxide is a molecule, or formula unit, I should say. Okay, so if you got all those correct, then well done. Okay, so let's answer these questions about moles. The table shows the masses of 9 samples of different elements. And it says draw a circle around each sample that contains the same number of atoms in as 12 grams of carbon. And then B, draw a square around each sample that contains the same number of atoms as 24 grams of carbon. And then C, do each of the remaining samples contain the same number of atoms? Explain how you worked out your answers to A, B, and C. Okay, and it's got a table on the side saying that the elements helium, carbon, and magnesium have a relative atomic mass of helium 4, carbon 12, and magnesium is 24. If we were to draw a circle around each sample that contains the same number of atoms in 12 grams of carbon, we know that carbon has a relative atomic mass of 12, so we weighed out 12 grams of it, that would be 1 mole. And so magnesium also has a relative atomic mass of 24. So if we weighed out 24 grams of it, that would also be 1 mole. Okay. And helium, if we weighed out 4 grams of helium, we would also have 1 mole of helium. Okay, so for the first one, masses in grams equals the relative atomic mass. You should have drawn a circle around 12 grams of carbon, 4 grams of helium, 24 grams of magnesium. If you weighed out, remember, if you weigh out the relative atomic mass of the element, you will have 1 mole of it, and there will be Avogadro's constant number of atoms in there, and they would all be the same. And it says draw a square around each sample that contains the same number of atoms as 24 grams of carbon. So 24 grams of carbon is twice the relative atomic mass. So that's 2 moles of it. And so if we doubled the helium and doubled the magnesium, they would also be 2 moles and have the same number of atoms as 24 grams of carbon. Okay, so we should have squared 48 grams of magnesium, which is double 24 grams, and 8 grams of helium, which is double 4 grams of helium. And do each of the remaining samples contain the same number of atoms? And so 6 grams of carbon is half the relative atomic mass of carbon, and 2 grams of helium is half the relative atomic mass of helium. So those two would have the same number of atoms. But magnesium, 8 grams of magnesium is 1/3 of the relative atomic mass of magnesium. So magnesium would be different. It would not contain half the number of atoms. It would have basically 1/3 of a mole. Okay. Okay, so now let's look at using Avogadro's constant. Okay, so many products are provided in packages of specific numbers, and these products can be referred to as fractions or multiples of the package they come in and still indicate a specific number. So, for example, we can we know that a dozen eggs, you've got 12 eggs in there. Okay, and if you've got half a dozen eggs, you've got 6 eggs. Okay, so we can do 12 times 0.5, which would give us 6 eggs. And if we've got 2 dozen eggs, we could do 12 times 2, which would give us 24 eggs. Okay, so a mole is used in a similar way, whereby Avogadro's constant 6.02 times 10 to the 23 particles per mole is used to package the particles. Okay, so a mole of sugar has precisely 6.02 times 10 to the 23 sugar particles. And a mole of salt has 6.02 times 10 to the 23 particles of salt or sodium chloride. Okay, so moles in a sample is equal to the number of particles divided by Avogadro's constant. Okay, so for example, a recycling center collected 2.3 million pen lids. Calculate the moles of pen lids at the recycling center. Give your answer to 2 significant figures. So a mole is equal to the particles, okay, the particle number divided by Avogadro's constant. Okay, and the particles in this case is the pen lids. Okay, so we got 2.3 million pen lids. So we can write that as 2.3 times 10 to the 6. Divide that by Avogadro's constant, 6.02 times 10 to the 23. And that would give us the number of moles. And so the number of moles would be 3.8 times 10 to the minus 18 moles of pen lids. And that's two significant figures. If we did another one, it is estimated that there are 7.5 times 10 to the 18 grains of sand on Earth. Calculate the moles of sand on all beaches and deserts of our planet. Give your answer to 2 significant figures. And so we know that the moles is equal to the number of, is equal to the particles divided by Avogadro's constant. Okay, so that would be 7.5 times 10 to the 18 divided by the Avogadro's constant, 6.02 times 10 to the 23. And that would give us the number of moles. And if we made it to 2 significant figures, that would be 1.2 times 10 to the minus 5 moles of sand grains. Okay, so chemists use moles to indicate a number of particles because it is simpler than referring to 6.02 times 10 to the 23 particles, or fractions or multiples. Okay, so particles in a sample is equal to the number of moles times Avogadro's constant. Okay, so we can calculate the number of particles that are present if we know the number of moles, and then we multiply that by Avogadro's constant. Okay, so one mole of salt is 1 times 6.02 times 10 to the 23. And that would give us the number of sodium chloride or salt particles present. And so if you had 0.1 mole of salt, then the number of particles that would be present would be 0.1 times Avogadro's constant, uh, which would give us 6.02 times 10 to the 22 salt particles present. Okay, so using this relationship, particles in a sample is equal to the number of moles times Avogadro's constant. It also allows chemists to calculate specific number of particles. So if we had 2 moles of sulfur, the number of particles present would be 2 times Avogadro's constant, which would give us 12.04 times 10 to the 23 atoms of sulfur. And if we had 0.25 moles of sulfur, then the number of sulfur atoms present would be 0.25 times Avogadro's number, which would give us 1.51 times 10 to the 23 atoms of sulfur. Okay, so calculate the number of moles of 5.47. Calculate the number of molecules in 5.47 moles of water. Give your answer to 3 significant figures. Okay, so the number of particles present is the moles times Avogadro's number. Okay, so the number of moles is 5.47, times that by Avogadro's number, which will then give you the number of molecules of water present, which rounded up to 3 significant figures is 3.29 times 10 to the 24 molecules of water. And calculate the number of molecules of 0.025 moles of oxygen. Give your answer to 3 significant figures. Okay, so the number of oxygen molecules is the number of moles times Avogadro's number. So that's 0.025 moles times Avogadro's number, which would then give us, rounded up to 3 significant figures, 1.51 times 10 to the 22 molecules of oxygen. It is important to state what particles we are referring to, whether it's atoms, molecules, or ions. And in this case, we are referring to molecules because the question states that the number of molecules. So if the mass of an individual object is known as well as the number present, then a collective mass can be calculated. So the mass of one piece of paper, for example, is 5 grams. How might you calculate the mass of a ream of paper? Well, we know that a ream of paper is 500 pieces of paper. So if we multiply the mass of one paper, which is five grams, by the total number of papers, which is 500. And then we get the collective mass of 2,500 grams. So chemists can use a similar process to predict the mass of a sample. So for example, if one atom of iron has a mass of 9.28 times 10 to the minus 23 grams, then calculate the mass of 1.5 moles of iron atoms. Give your answer to three significant figures. So first of all, if we know that the number of to calculate the number of particles present, we can simply take the number of moles, which is 1.5, and multiply that by Avogadro's number, and that will give us the number of atoms present. So 1.5 times 6.02 times 10 to the 23 is equal to 9.03 times 10 to the 23. And once we've got the number of iron atoms that are present, we then can simply multiply that by the mass of one atom of iron, which is 9.28 times 10 to the minus 23. And we will then get a mass of 83.8 grams of one atom of gold, and gold has a mass of 3.27 times 10 to the minus 22 grams. What is the mass of 0.75 moles of gold atom? And give your answer to three significant figures. So we would first need to work out the number of gold atoms that are present. So we could take 0.75 moles of gold and multiply that by Avogadro's constant. And once we've got the number of gold atoms, we can then multiply that by the mass of one atom, which is 3.27 times 10 to the minus 2. Okay, so in 0.75 moles of gold, we have the number of atoms present is 4.52 times 10 to the 23. And then we can work out the mass of the total number of atoms by multiplying that by the mass of one atom of gold, which is 3.27 times 10 to the 22. And we get our answer as 148 grams, which is rounded up to three significant figures. Okay, so let's calculate the number of particles in each sample. Give your answer to three significant figures. If you got 3.5 moles of iron, and B 0.32 moles of sodium chloride, and C 0.84 5 moles of carbon dioxide, calculate the number of particles. And so for each one of those, calculate the number of particles in that amount of moles. We would simply need to multiply each of the moles by Avogadro's constant. Okay, so 3.5 moles of iron times the Avogadro's constant would give us 2.11 times 10 to the 24 iron particles. And for B, 0.32 moles of sodium chloride multiplied by Avogadro's constant would give us 1.93 times 10 to the 23 particles of sodium chloride, and 0.845 moles of carbon dioxide multiplied by Avogadro's constant would give us 5.09 times 10 to the 23 particles of carbon dioxide, all rounded up to three significant figures. And notice we gave our answers in particles because it simply says in the question, it says calculate the number of particles in each sample. If it said calculate the number of atoms or the number of molecules, we would give our answer in molecules or atoms. And this one for question 2, it says calculate the number of moles of each sample. Give your answer to 3 significant figures. And so you've got 6.09 times 10 to the 23 atoms of helium. And you've got 7.51 times 10 to the 24 molecules of methane. And 5.3 times 10 to the 22 formula units of magnesium oxide. So we need to calculate the number of moles. And what we would simply do is to calculate the number of moles, we can simply divide these number of atoms, molecules, and formula units. We can simply divide them by Avogadro's constant. Okay, so for A, we can simply divide 6.09 times 10 to the 23 by Avogadro's constant to give us 1.0, sorry, oh, sorry, 61.01 moles of helium. And for B, 7.51 times 10 to the 24 divided by 6.02 times 10 to the 23 would give us 12.5 moles of methane, and 5.3 times 10 to the 22 divided by 6.02 times 10 to the 23 would give us 0.0880 moles of magnesium oxide. So if you got all of those correct, then well done. And the next one is calculate the mass of each sample. Give your answer to 3 significant figures. If you're given 0.22 moles of gold, 1 atom of gold has a mass of 3.27 times 10 to the minus 2 grams. And B, 1.5 moles of magnesium, 1 atom of magnesium has a mass of 3.98 times 10 to the minus 3 grams. And C, 0.76 moles of magnesium oxide. 1 formula unit of magnesium oxide has a mass of 6.69 times 10 to the minus 23. It says calculate the mass. So in this instance, what we would need to do is we would first need to work out how many particles are present in the moles that are given. So we multiply it by Avogadro's, multiply the moles by Avogadro's number. That will give us the number of particles present. And then we can, once we've got the number of particles, then we can multiply each of the particles by the mass that is given. Okay, so for gold, we got 0.22 moles, so we multiply that by Avogadro's constant to give us 1.3244. And then once we've got the number of particles present, we can then multiply it by the mass of gold, a gold atom, to give us 43.3 grams would be the mass of gold present. And 1.5 moles of magnesium, multiply that by Avogadro's number. And once we've got the number of magnesium atoms present in 1.5 moles, we then can multiply that by the mass of 1 atom of magnesium. And that would then give us 35.9 grams of magnesium. And for magnesium oxide, 0.76 moles of it, multiply that by Avogadro's constant to give us the number of magnesium oxide molecules that are present, and then we can multiply it by the mass of a magnesium oxide particle or molecule to give us 30.60 uh, grams. Okay, so in summary, chemicals are measured in moles, which is defined as Avogadro's constant number of particles. And so 1 mole is equal to 6.02 times 10 to the 23 particles. And remember, when we say particles, particles could be atoms, molecules, or formula mass or ions. Okay, it is important that we state which one we are referring to. And the number of particles can be atoms, ions, or molecules. And in 1 mole of a substance does not change. Okay, so 1 mole of a substance is always going to be the substance is relative atomic mass. And Avogadro's number can be used to calculate the number of particles in moles of a substance and vice versa. And the mass of 1 mole of an element is equal to the relative atomic mass of the element, but that is measured in grams. Okay, so hopefully this lesson was useful to you and you understand a bit better about moles. I do hope to see you on our next science lesson.